please subscribe to support the channel. What existed before everything began? It's a question that cuts to the heart of existence itself, haunting, fascinating, and almost impossible to grasp. The Big Bang, around 13.8 billion years ago, wasn't an explosion in space, but the moment when space and time themselves begin to expand from an unimaginably hot, dense state. Every galaxy, every atom, every second that has ever passed traces back to that instant. Yet, when we ask what came before it, we're forced to confront a mystery that defies ordinary thinking. Because if time was born with the Big Bang, can before even exist? This question pushes science and philosophy to their limits, inviting us to explore not just how the universe began, but what reality itself truly means. The Big Bang, it's one of those terms that instantly conjures the image of a colossal explosion, a blast of unimaginable power that hurled galaxies into the void. But that mental picture, vivid as it is, misses the true wonder of what scientists actually mean by the Big Bang. It wasn't an explosion in space, it was an expansion of space itself. There was no central point where it all began, and no empty void waiting to be filled. Instead, space, time, energy, and matter all began expanding together, everywhere, at once. Every point in the universe was the center, because the universe itself was unfolding from within. In that first, unimaginable moment, a fraction of a second after time itself began, the universe was a seething ocean of energy, hotter and denser than anything we can replicate or even truly imagine. Temperatures soared beyond 1 trillion degrees, and the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, may have been unified into one single cosmic force. Within this fiery haze, particles flickered into being and vanished again, colliding and combining in an endless dance of creation and annihilation. In less than a heartbeat, this dense, energetic cosmos began to stretch, cooling as it expanded. To the human mind, it's almost impossible to comprehend. There was no outside for the universe to expand into because outside didn't exist. The Big Bang was not like a bomb going off in the sky. It was more like the surface of an inflating balloon where every point moves away from every other point as the balloon grows. If you were standing on that surface, you would see everything moving away from you equally, just as we observed galaxies receding from us today. And just as the balloon's surface stretches, the very fabric of space has been stretching ever since. That's why distant galaxies appear to be racing away from us. Not because they're flying through space, but because the space between us and them is growing. It was in the 1920s that astronomers like Edwin Hubble provided the first compelling evidence for this expansion. By observing the redshift of distant galaxies, the way their light stretches into longer, redder wavelengths, Hubble showed that the farther away a galaxy is, the faster it appears to be receding. This discovery turned our understanding of the cosmos on its head. It meant the universe was not static and eternal, as once thought, but dynamic. It had a history, a beginning, and perhaps even an end. Later, the faint afterglow of that fiery birth, known as the cosmic microwave background radiation, was discovered. A relic light still bathing the cosmos, a whisper from that ancient moment of creation, now cooled to just a few degrees above absolute zero. When scientists trace the expansion backward, the equations of general relativity lead to a startling conclusion. Everything, every star, every planet, every particle was once compressed into an incredibly small, dense region. Not a point in space, but a state where space itself was curved to the extreme, where density and temperature were so high that the laws of physics, as we know them, begin to fail. This is where the term Big Bang truly earns its name. Not as an explosion, but as the moment when the very structure of reality began to unfold from a singular, indescribable condition. But the Big Bang Theory doesn't describe the moment of creation itself. It's a model of the universe's evolution, not a theory of its origin. It tells us how the universe expanded and cooled, how matter formed, how stars ignited, how galaxies clustered and evolved, but it doesn't tell us what set it all in motion. It's like watching the ripples spreading across a pond without knowing what dropped the stone. And that's where the mystery deepens. Because when we try to look back all the way to the very beginning, to the instant of zero time, our equations break down. The mathematics that so elegantly describe the universe cease to make sense. Infinity creeps into our calculations. Density, temperature, and curvature all rise without limit, pointing to a place where physics itself simply stops working. That moment, the Planck epoch, about 10 to the power of negative 43 seconds after the Big Bang, stands as the boundary between what we can know and what remains beyond our reach. So when we talk about the Big Bang, we're really talking about everything that has happened since that earliest fraction of a second. We can map how hydrogen formed, how the first stars lit up, how galaxies clustered and evolved, but what happened before the universe became describable? What was it like in that unknowable sliver of time before 10 to the negative 43 seconds when the laws of physics were fused into something beyond our comprehension? Was there a true beginning? Or was the Big Bang just a transition from something even more ancient?
These are the questions that lead us to the next step in our exploration, the limits of our knowledge. Because before we can talk about what came before the Big Bang, we have to face the sobering truth that our most powerful scientific tools, relativity, quantum theory, cosmology, all reach a breaking point when we approach that cosmic boundary. The deeper we go, the more we confront the limits, not only of our instruments, but of our very understanding of space, time, and existence itself. There is a frontier in our understanding of the universe that stands like a wall of fog, a boundary we cannot yet see through no matter how advanced our mathematics or how powerful our telescopes become. That frontier is known as the Planck time, roughly 10 to the minus 43 seconds after the Big Bang. To grasp how small that is, imagine splitting a single second into a trillion pieces, and then splitting each of those pieces into another trillion. You'd still be nowhere close to the Planck time. It's the smallest measurable unit of time that physics can meaningfully describe, the threshold where our current theories lose their grip on reality. Up until this unimaginably brief instant, our understanding of the cosmos is guided by two great pillars of modern science: Einstein's general theory of relativity and quantum mechanics. Relativity describes the universe on the grand scale: stars, galaxies, gravity, the curvature of space and time. Quantum mechanics governs the microscopic world: atoms, particles, and the mysterious fluctuations that define the subatomic realm. Each works beautifully in its own domain, but when we try to combine them, when we attempt to apply both to the universe at its very birth, where the entire cosmos was smaller than an atom and denser than any known object, the equations simply break. It's not that the Big Bang was chaotic in a way we can't yet compute, it's that the mathematics itself refuses to cooperate. As we approach that singular moment, our equations predict infinities, infinite density, infinite temperature, infinite curvature of space-time. In physics, infinity doesn't describe a real thing. It's a sign that something's gone wrong, that our theories are being stretched beyond their limits. It's as if we're trying to use the classical physics to describe what happens inside a quantum particle. The language itself becomes meaningless. At times earlier than 10 to the minus 43 seconds, the gravitational force would have been as strong as the other fundamental forces of nature. Space and time themselves would have been fluctuating quantum fields, not the smooth, continuous fabric that relativity describes. This means that the very foundation of reality, the geometry of space-time, wasn't fixed, but uncertain. Imagine a world where before and after blur together, where cause and effect no longer follow the familiar flow of time. That's the kind of universe we enter when we cross the Planck boundary. Scientists often describe this epoch as the quantum gravity era, a period where both gravity and quantum effects were equally important, but where no complete theory yet exists to unify them. We've tried, of course. String theory, loop quantum gravity, and other models attempt to bridge this gap, but none have yet produced definitive, testable predictions. Until we have such a theory, a true theory of everything, the universe before the Planck time remains shrouded in mystery. What makes this limit so fascinating is that it's not just a technical roadblock, it's a philosophical one. The Planck time doesn't merely mark a point we can't yet observe, it might mark the beginning of observation itself. Beyond it, the concepts we rely on, space, time, energy, even the distinction between something and nothing, may have no meaning. Our scientific instruments can't look back that far because there were no photons, no light, no structure for light to travel through. The cosmic microwave background, that faint echo of the Big Bang, was released about 380,000 years after the event, and yet we can mathematically reconstruct much of what happened before that. But when we reach the Planck time, we hit a wall of ignorance, not because we aren't clever enough, but because the universe itself was in a state beyond the reach of our current laws. And yet the human mind refuses to stop there. We ask, what lies beyond that wall? What was happening before 10 to the minus 43 seconds, when the universe was less than a grain of possibility? Was there a before at all? Or was time, as we understand it, born alongside space and energy, emerging from a deeper, timeless reality? To many physicists, this question isn't just unanswerable yet, it might be unaskable in the traditional sense, because to ask what came before assumes that time existed to measure a before and after. But if time itself began at the Big Bang, then beyond that point, there was no before, no ticking clock, no changing state. The very concept of earlier dissolves. This realization shakes the very foundation of how we think. It forces us to confront a universe that may not have a beginning in the way we imagine beginnings to work. Still, even with this boundary in place, science pushes forward. Experiments at the Large Hadron Collider, deep space observations from the James Webb Telescope, and theoretical research in quantum gravity all aim to peel back more of this cosmic curtain. Some cosmologists even believe that remnants of the Planck era, tiny gravitational waves or subtle patterns in cosmic radiation, might still be detectable, whispering clues about what came before time itself began to flow. But for now, that first 10 to the minus 43 seconds remains the most enigmatic instant in history, the point where our knowledge fades into the unknown. It's the edge of the cosmic map, marked with a warning older than science itself. Here be mysteries. And it is precisely at this edge that our next question emerges, one that twists both language and logic. If time and space began with the Big Bang, then what does it even mean to ask what came before? This is the before problem, and it challenges not just our physics, but the very structure of human thought. When we reach the question, what was before the Big Bang, we are stepping into a territory where language, logic, and even imagination begin to crumble. It feels like such a natural question to ask. After all, everything we know in our everyday experience has a before and an after. Every sunrise follows a night. Every birth follows a gestation. Every action follows a cause. Our minds are wired to think in terms of sequences, timelines, and progression. So it seems only natural to ask, if the universe began with the Big Bang, what came before it? What caused it? What set it into motion? But here's where the universe defies intuition. According to our best scientific understanding, drawn from Einstein's theory of general relativity and supported by decades of cosmological observation, time itself began with the Big Bang. In other words, asking what came before the Big Bang is like asking what's north of the North Pole. It's not that there's something hidden up there we haven't found yet, it's that the question itself doesn't quite make sense, because north stops being meaningful at that point. Likewise, before stops being meaningful when we reach the moment the universe began. This is what makes the before problem so profound. It reveals that the human way of thinking, bound as it is by the flow of time, may not be adequate to comprehend the origins of everything. Our brains evolved to track moments, to remember the past and anticipate the future. But if time itself had a beginning, then there was no before in which anything could happen.
no cause that could precede the effect of the Big Bang. The Big Bang, then, wouldn't just be the beginning of the universe, it would be the beginning of beginnings themselves. To understand why this idea arises, we have to return to what Einstein showed us in 1915 with his general theory of relativity. He demonstrated that space and time are not independent, separate entities. They are woven together into a single four-dimensional fabric called spacetime. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move. This elegant union means that wherever there is space, there is also time. They are inseparable partners. So if space came into existence at the Big Bang, as cosmology tells us it did, then time must have come into existence along with it. This means that the Big Bang wasn't just the start of the universe's expansion, it was the birth of time itself. Before that moment, there was no ticking clock, no sequence of events, no framework within which anything could happen. The very notion of before presupposes a temporal dimension, and when that dimension doesn't exist, the word loses meaning. It's a concept that can make even seasoned scientists pause, because it forces us to admit that our deepest intuitions about cause and effect might not apply at the ultimate beginning. And yet, this is deeply unsettling to us. We're used to the idea that everything must have a cause. Every fire needs a spark, every ripple needs a stone, every birth needs a parent. To think that the universe simply began without anything preceding it feels unnatural, almost incomprehensible. But maybe that's not the universe's problem, maybe it's ours. We may be like fish trying to understand what water is, so immersed in time that we can't imagine existence without it. To illustrate this, imagine a two-dimensional creature living on the surface of a balloon. To that creature, north and south exist, but up does not. It has no meaning within its flat world. Now imagine the balloon being inflated. From the creature's perspective, everything is moving away from everything else. Its world is expanding. But if the creature asks, what was the surface of the balloon before it existed? There's no answer that makes sense within its frame of reference. The before of the balloon's surface lies outside the very dimensions it inhabits. Similarly, for us, the before of time lies outside the temporal dimensions we experience. Some cosmologists and philosophers, however, argue that while before may not exist in the temporal sense, there could still be a state or condition that somehow preceded the Big Bang, not in time, but in a different kind of existence altogether. Perhaps there was a timeless quantum realm, a field of potential energy waiting to transition into the dynamic universe we know. Or perhaps, as some theories suggest, the Big Bang wasn't the beginning of everything, but just a transformation of something that had always existed in another form. But within the framework of classical cosmology, we hit an impassable barrier. The very equations that describe the expansion of the universe, the Friedmann equations, derived from general relativity, lead us back to a singular point where the density becomes infinite and time effectively stops. That singularity marks not only the beginning of the universe, but the boundary of meaningful time. Beyond it, the very coordinates of space and time lose definition. This is what makes the before problem not just a physical puzzle, but a philosophical one. It blurs the line between scientific inquiry and metaphysical speculation. Science, by its nature, deals with cause and effect, with processes that unfold within time. But if the origin of time itself is the subject, then we're dealing with a reality that transcends causality as we understand it. We can no longer ask what caused the universe in the traditional sense, because the concept of cause requires time, and time begins with the universe. Still, this doesn't mean the question is meaningless, only that we must rethink what we mean by before. Maybe the before of the universe wasn't temporal, but structural, a state of potential being from which space-time itself emerged. Maybe the universe wasn't created in time, but with time, in the same way a melody doesn't exist without rhythm. And maybe, just maybe, our need for before is simply the echo of our own limited perspective, bound by the arrow of time we experience. This realization leads naturally into Einstein's deeper insight, that time and space are not separate and that their intertwined nature means the birth of one is the birth of the other. To truly understand why there might not have been a before, we must explore what it means that the universe is not just a collection of things in space, but a vast, dynamic geometry of space-time itself, a fabric that was born, stretched, and continues to evolve. Einstein forever changed the way we think about the universe. Before his work, people imagined space and time as separate, unchanging backdrops, the stage upon which the events of the cosmos unfolded. Space was thought to be an infinite emptiness stretching in every direction, and time was an eternal clock ticking steadily forward, indifferent to what happened within it. But Einstein shattered that picture. He revealed that space and time are not independent. They are woven together into a single, flexible fabric called space-time. And that insight carries a profound consequence. If space had a beginning, then time must have begun with it. Einstein's theory of general relativity, published in 1915, was more than a new description of gravity. It was a revolution in how we understand reality itself. According to the old Newtonian view, gravity was a force that pulled objects together. The sun pulled the Earth into orbit, the Earth pulled the moon, and so on. But Einstein saw gravity not as a force, but as a geometry. Massive objects like stars and planets curve the fabric of space-time around them, and that curvature tells objects how to move. The Earth doesn't orbit the sun because it's being pulled, it moves along the curved path that space-time creates in the sun's presence. This merging of space and time into one dynamic entity means that you can't change one without affecting the other. If you move quickly through space, you experience time more slowly, a phenomenon known as time dilation, proven by experiments with atomic clocks and high-speed particles. Gravity, too, bends time. Near a massive object, time flows more slowly than it does farther away. That's not science fiction. GPS satellites, for example, have to account for both gravitational and velocity-based time dilation to give us accurate positions on Earth. But when we apply Einstein's insight to the entire cosmos, something extraordinary happens. If space itself is expanding, as Hubble's observations confirmed, then time must be expanding along with it. This means that both space and time have a shared origin, a moment when the entire space-time continuum emerged. The Big Bang, then, wasn't an explosion in space, it was the creation of space-time itself. When we trace that expansion backward through the equations of general relativity, we reach a point where space and time both collapse into what's known as a singularity, a point where the curvature of space-time becomes infinite and the known laws of physics cease to operate. At that singularity, all conventional notions of space, time, and causality break down. There was no before the Big Bang because before requires time, and time itself was born in that instant. This is one of the most counterintuitive yet essential ideas in modern cosmology. Time is not an external river flowing endlessly. It is part of the universe, rising and evolving along with the cosmos itself. The universe is not in time, the universe contains time. To visualize this, imagine the surface of a balloon again, representing the fabric of space-time. As the balloon inflates, every point on its surface moves away from every other point. That's the expansion of the universe. Now, if you trace the balloon's surface backward, you don't reach a point in space, you reach a state where the surface itself disappears. The beginning of the expansion is not a place in the balloon, it's the moment the balloon began to exist. In the same way, the Big Bang wasn't a point in space where everything exploded, it was the moment space-time itself came into existence and began to stretch. This also means that time is relative, not just to speed or gravity, but to the structure of the universe itself. Every observer, every galaxy, every particle carries its own version of time, its own clock shaped by its movement through the fabric of space-time. From our vantage point, we measure the age of the universe as about 13.8 billion years, but that measurement is bound to the way time flows in our region of space-time. In other parts of the universe, under different gravitational conditions or during different eras of cosmic expansion, time could have flown differently. Einstein's conception of spacetime also reshaped our understanding of beginnings and endings. In general relativity, spacetime can be curved not only by matter but also by energy, including the mysterious dark energy that's driving the accelerated expansion of the universe today. This curvature suggests that the universe's geometry can have many possible forms: open and infinite, closed and finite, or something more complex. But in each case, space-time itself remains the arena in which reality unfolds. Without space-time, there is no where and no when, no distance, no duration, no before or after. It's a concept so simple and yet so profound that it's almost impossible to internalize. We tend to think of ourselves as moving through time, but in Einstein's vision, we are static in a four-dimensional space-time, with our past, present, and future all existing as part of a single cosmic tapestry. Time, as we experience it, flowing like a river from past to future, might just be the way our brains perceive movement along this four-dimensional surface. The Big Bang, then, represents not the start of that river, but the lower boundary of the entire landscape. And this leads to one of the deepest insights that cosmology has given us. The universe does not exist in time. Time exists because of the universe. The birth of space and the birth of time were the same event. Before that, there was no ticking clock, no expanding distance, no change, because there was no space-time for change to occur within.
But Einstein's theory, as revolutionary as it was, also leads us into a new mystery, one that modern physics has wrestled with ever since. When we follow his equations back to that first instant, they predict a singularity, an infinitely small, infinitely dense point where all the fabric of space-time collapses. Yet, infinities are red flags in physics. They signal that our theories have reached their limit. So, if Einstein's framework leads us to a singularity, perhaps that means it's incomplete. Maybe there was never a true singularity at all. Maybe something else was happening at the very beginning, something beyond Einstein's reach. That realization gave birth to the next great question in our journey through cosmic origins, the question of the singularity itself. Did the universe really begin from an infinitely dense point, or is that just a sign that our understanding is missing a crucial piece of the puzzle? The concept of the singularity sits at the very heart of traditional Big Bang cosmology, a haunting and elegant idea that the entire universe, with its countless galaxies and endless stretches of space and time, once existed as a single, infinitely dense point. According to Einstein's equations, if you rewind the cosmic clock far enough, every galaxy, every particle of matter and energy, every field and force, all converge into a vanishingly small region where the curvature of space-time becomes infinite. This point, called the singularity, would mark not just the beginning of the universe, but the breakdown of everything we understand about physics. It's a breathtaking concept. Imagine compressing everything, every atom, every star, every black hole, every law of nature into something smaller than the head of a pin, smaller than a grain of dust, smaller even than the tiniest quantum particle. At that scale, density and temperature soar beyond all conceivable limits. Space and time themselves lose their meaning. There is no inside or outside, no before or after. Everything is crushed into an infinitesimal point where our equations simply stop working. This idea of the singularity first emerged naturally from Einstein's general relativity. When cosmologists like Alexander Friedmann and Georges Lemaitre began solving Einstein's equations in the 1920s, they found that the universe couldn't be static. It had to be either expanding or contracting. If it's expanding now, then tracing that expansion backward implies a moment when all distances were zero, a mathematical singularity where the curvature of space-time becomes infinite. In the mid-20th century, this theoretical prediction gained credibility through observational evidence. Edwin Hubble's discovery that galaxies are moving away from each other, and later, the detection of the cosmic microwave background radiation,
the leftover heat from the Big Bang itself. For decades, scientists accepted this singularity as the universe's true beginning, a kind of cosmic birth point. Stephen Hawking and Roger Penrose even proved mathematical theorems in the 1960s, showing that under very general conditions, any universe governed by general relativity and containing matter that attracts itself, like ours, must have started from a singularity. In this view, the Big Bang singularity wasn't just a curiosity, it was inevitable. But there's a problem with infinities. In physics, infinity doesn't describe a physical reality. It's a sign that our theory has reached its limit. The singularity, rather than being a literal object or event, might instead represent a boundary of knowledge, the point where our current equations break down. It's not necessarily that the universe was infinitely dense, but that our mathematical tools fail to describe what was really happening at that scale. Einstein's general relativity, though remarkably successful at describing the motion of planets and the structure of the cosmos, is a classical theory. It doesn't take into account the jittery, probabilistic nature of the quantum world. Near the singularity, where densities and energies are unimaginably high, quantum effects can no longer be ignored. The problem is that relativity and quantum mechanics are built on very different principles. Relativity describes a smooth, continuous spacetime. Quantum mechanics deals with discrete, uncertain probabilities. When we try to merge the two, they clash violently, producing nonsense, infinities, paradoxes, and undefined quantities. So modern physicists now suspect that the singularity is not a real physical thing, rather a symptom of trying to use an incomplete theory to describe a realm where it no longer applies. To truly understand what happened at the beginning, we need a theory of quantum gravity, a framework that seamlessly unites relativity's space-time geometry with quantum mechanics' probabilistic rules. Only then can we know what replaced the singularity at the dawn of time.
In recent decades, many ideas have been proposed. Some scientists believe that at incredibly small scales, space and time aren't smooth at all, but made up of discrete, quantized units, the smallest possible chunks of reality. In that view, the universe can't compress into an infinitely dense point because there's a limit to how small space-time can be. Others propose that the Big Bang wasn't a true beginning, but a transition, perhaps the end of a previous universe that collapsed in a big crunch and then rebounded in what's now called a big bounce. In those models, the singularity is replaced by a bounce, a moment when the collapse of one cosmos turns into the expansion of another. Another school of thought comes from string theory, which suggests that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings of energy. In string theory, there's no such thing as an infinitely small point. The strings have a minimum length, the Planck length, below which the concept of smaller loses meaning. That means the universe could never shrink into an actual singularity. Instead, it would reach a smallest possible size and then expand again. Even Stephen Hawking himself began to move away from the strict singularity concept later in his career. Along with James Hartle, he proposed the no-boundary model, which suggests that the universe doesn't have a sharp beginning or a point of creation, but rather a smooth, finite structure, somewhat like the surface of the Earth. You can travel south until you reach the South Pole, but you can't go farther south, not because there's a wall there, but because the concept of south simply ends. In the same way, time could curve smoothly into the early universe, meaning there was no before and no singularity where the laws of physics break down. Still, the singularity remains a powerful idea, both scientifically and symbolically. It represents the edge of our understanding, the point where all our theories converge and collapse under their own weight. It's a reminder that even our most successful scientific frameworks are temporary scaffolds, built to reach toward truth but not yet touching it. The singularity is a mirror reflecting our ignorance as much as our knowledge, a cosmic question mark at the foundation of reality. But even if the singularity as a literal entity is now in doubt,
It opened the door to some of the most creative and daring ideas in modern science. If the classical laws of physics break down at that moment, perhaps a new set of laws takes over. Laws ruled by quantum mechanics, uncertainty, and probability. And so, to peer deeper into the earliest moments of existence, we must now turn to the strange, shimmering world of the quantum, a world where chance reigns supreme, where particles pop in and out of existence, and where the entire universe itself might have flickered into being from the quantum void. When we push our understanding of the universe back to its earliest conceivable moment, that almost mythical instant when everything we know is compressed into a state beyond comprehension, classical physics begins to crumble. Einstein's elegant description of curved spacetime falters in the face of infinite density and infinite curvature. To move beyond that boundary, we need to enter an entirely different realm, the world of the quantum, where certainty dissolves into probability, and reality itself seems to flicker between being and nothingness. Quantum mechanics, born in the early 20th century, was not just another branch of physics. It was a revolution in how we think about the universe at its most fundamental level. In the classical world of Newton and Einstein, objects have definite positions, motions, and properties. Planets follow predictable orbits, billiard balls collide according to clear, calculable rules. But in the quantum world, certainty vanishes. A particle doesn't have a definite location until it's observed. Its energy, momentum, and even existence are governed by probability waves, which describe not where the particle is, but where it might be. Reality at this scale isn't fixed. It's fluid, indeterminate, constantly fluctuating between possibilities. This is the framework that must have ruled the universe in its infancy. When the cosmos was smaller than a proton and hotter than any conceivable furnace, the classical rules of physics could not possibly apply. The universe wasn't yet a well-defined structure of space and time. It was a swirling quantum foam of probabilities, where energy and matter were interchangeable, and where the very geometry of space-time itself was uncertain. Imagine an existence so volatile that even the distinction between something and nothing loses meaning, where the entire universe could emerge from a flicker in the vacuum and vanish just as quickly. In this quantum realm, uncertainty isn't a limitation, it's a fundamental property of nature. The Heisenberg uncertainty principle tells us that the more precisely we know one property of a particle, like its position, the less precisely we could know another, like its momentum. This uncertainty is not due to measurement error or lack of technology. It's woven into the fabric of reality itself. And this same principle, when applied to the early universe, leads to profound implications. It means that the birth of the cosmos may not have been a neat, orderly event, but rather a quantum fluctuation, a spontaneous emergence driven by the restless energy of the quantum vacuum.
The idea that the universe could have been born from quantum mechanics is both mind-bending and strangely poetic. In quantum physics, virtual particles constantly appear and disappear, borrowing energy from the vacuum for incredibly brief moments before annihilating one another, in perfect balance with the laws of energy conservation. This borrowing happens everywhere, all the time, even in the emptiest regions of space. What we call empty space is anything but empty. It's a seething, vibrant field of potential energy, constantly bubbling with fleeting bursts of creation and destruction. Some physicists, like Edward Trayon in the 1970s, took this principle to its cosmic extreme and proposed that perhaps the entire universe is just one enormous quantum fluctuation, a temporary bloom of energy that, for reasons we don't yet understand, became stable and began to expand instead of collapsing back into nothingness. This line of thought offers a profound reinterpretation of the Big Bang. Instead of being the creation of everything from a singular point, it might have been a quantum event, a natural consequence of quantum laws acting on a pre-existing vacuum state. The quantum universe, in its earliest instant, would have been a probabilistic storm where space-time itself flickered in and out of existence, where no definite geometry existed,
and where the boundaries between before and after were meaningless. What we call the Big Bang could have been a transition, a quantum tunneling event in which the universe leapt from a timeless quantum state into the expanding space-time we now inhabit. Quantum mechanics also introduces the notion of wave function, a mathematical object that encodes all possible states of a system. When we observe the system, the wave function collapses, selecting one particular outcome from among the many possibilities. But before observation, all possibilities exist simultaneously in a state of superposition. If we extend this idea to the universe as a whole, we arrive at a staggering implication. The early universe may have existed as a vast superposition of possible realities, countless potential universes, each with different laws, dimensions, or initial conditions, until one particular configuration became our observable cosmos. This is not just speculation. It arises naturally from quantum cosmology, where physicists like Stephen Hawking and James Hartle have used the mathematics of quantum wave functions to describe the entire universe. In this framework, time itself is not fundamental. It's emergent. The early universe wasn't evolving in time. Rather, time was one of the outcomes of quantum processes that stabilized as the universe cooled and expanded. Before that, there was no distinction between past and future, cause and effect. Everything that would ever happen existed as a quantum potential, timeless and undifferentiated. The flow of time, the arrow that carries us from birth to death, from cause to consequence, only appeared later as the universe grew large enough for classical physics to take over. This shift from the deterministic clarity of Einstein's relativity to the shimmering uncertainty of quantum mechanics marks one of the greatest conceptual leaps in human thought. It tells us that at the deepest level, reality is not a rigid clockwork, but a tapestry of probabilities, one in which even the universe itself could have been born not from inevitability, but from chance. Of course, chance here doesn't mean randomness in the chaotic, purposeless sense. In quantum mechanics, chance is structured, governed by precise mathematical rules. The universe didn't just pop out of nothing in the ordinary sense. It emerged from the quantum vacuum, a state filled with potential energy and governed by laws that allow for spontaneous fluctuations. Whether one calls that nothing or something depends on how deeply one defines existence itself. As physicists began to explore this quantum landscape, they soon realized that the idea of the universe emerging from quantum processes wasn't just philosophical speculation. It could actually be modeled mathematically. This led to one of the most fascinating and controversial ideas in all of cosmology, the quantum fluctuation hypothesis, which suggests that our entire universe may have originated from a brief, spontaneous disturbance in a quantum field, a blip in the eternal sea of potentiality that somehow became real, stable, and vast beyond comprehension.
In quantum mechanics, the concept of nothing isn't truly nothing. Even in what we might imagine as a perfect vacuum, a region devoid of matter, radiation, or light, the laws of quantum physics tell us that energy is never completely at rest. Beneath the apparent stillness of emptiness lies a restless ocean of potential, constantly roiling with spontaneous fluctuations. Particles and antiparticles flicker into being for the briefest moments, borrow energy from the vacuum, then annihilate one another and disappear, returning the balance of the universe to zero. These ephemeral appearances are called quantum fluctuations, and they've been observed and verified countless times in particle physics. Now, imagine taking that principle, the idea that tiny bursts of energy can spontaneously emerge from a vacuum, and scaling it up to the entire cosmos. This is the essence of the quantum fluctuation hypothesis, the idea that the universe itself could have arisen from one of these spontaneous fluctuations in a pre-existing quantum vacuum. In this view, the Big Bang wasn't the beginning of absolute nothingness becoming something. It was the moment a quantum blip expanded, stabilized, and evolved into the vast cosmic structure we inhabit today. This idea, while radical, emerges naturally from the mathematics of quantum field theory. According to Heisenberg's uncertainty principle, the more precisely we try to define the energy of a region of space, the less precisely we can define the duration for which that energy exists. That means that energy can spontaneously appear, as long as it doesn't stick around too long. Nature allows tiny borrowing of energy from the vacuum, as long as it's paid back quickly. For subatomic particles, this borrowing happens constantly, on scales too small for us to notice. But what if, by some mechanism, a quantum fluctuation didn't fade away? What if it lasted long enough to inflate, to grow exponentially, powered by its own energy field, and become a self-sustaining universe? That's the extraordinary idea proposed by physicists such as Edward Tryon, Alan Guth, and others who developed the modern theory of cosmic inflation. In 1973, Tryon suggested that our universe could literally be a quantum fluctuation of nothing. He argued that the total energy of the universe might, in fact, be exactly zero, with the positive energy of matter balanced perfectly by the negative energy of gravity. In that case, the creation of the universe wouldn't violate any physical laws, because the net energy would remain zero. It would be the ultimate cosmic free lunch. From this perspective, the universe didn't emerge from nothing in violation of physics, but in perfect obedience to it. Here's how this could work. In quantum field theory, the vacuum isn't empty space. It's a field with a minimum energy level, filled with potential for fluctuations. Occasionally, a fluctuation large enough could distort that field, creating a bubble of energy. If the conditions were right, that bubble could undergo a phase transition, similar to how water vapor condenses into liquid, releasing energy that triggers a rapid expansion. That rapid expansion, known as cosmic inflation, could then stretch the tiny quantum bubble to cosmic proportions, smoothing out its irregularities and creating a uniform universe like the one we observe today. At first glance, this seems almost absurd. The idea that an entire universe could just pop into existence from a quantum ripple in a vacuum field. Yet the mathematics behind it is consistent with what we know of quantum physics. The universe doesn't need a pre-existing space to expand into. It creates space as it expands. And because time itself is part of the structure of the universe, there's no need to ask when the fluctuation happened or what came before. The moment of creation defines the beginning of time itself. The deeper beauty of this idea lies in its self-consistency. If the total energy of the universe truly sums to zero, then the creation of a universe doesn't cost anything in physical terms. Positive energy, the mass and radiation that fill the cosmos, is exactly counterbalanced by the negative energy stored in the curvature of spacetime due to gravity. The universe could emerge spontaneously, expand, and persist indefinitely, all while respecting the fundamental conservation laws. As Stephen Hawking once famously put it, because there is a law such as gravity, the universe can and will create itself from nothing. This doesn't mean that nothing is truly nothing, though. The quantum vacuum is not a void of absence, but a kind of pre-existence, a field brimming with potential energy, fluctuations, and uncertainty. It's the stage upon which the quantum rules operate, a sea of possibilities where reality can momentarily bubble into being. In this sense, the phrase, "the universe came from nothing," is misleading. The nothing here is a quantum nothing, full of latent structure and governed by physical laws. It's a reality where the boundary between existence and non-existence blurs, and where the universe could emerge naturally as one of countless possible fluctuations. The quantum fluctuation hypothesis also offers an intriguing explanation for why the universe appears so finely tuned and uniform. During the earliest moments, quantum fluctuations would have been stretched by cosmic inflation, seeding the variations in density that later grew into galaxies, stars, and planets. In other words, the very imperfections of the quantum world, those tiny, random blips of energy, became the blueprint for the cosmic structures we see billions of years later. The galaxies that light up the night sky are quite literally
the magnified fingerprints of quantum uncertainty. But this hypothesis also opens a philosophical Pandora's box. If our universe could emerge from a quantum fluctuation, what's to stop countless other universes from doing the same? If the quantum vacuum can produce one bubble of spacetime, why not many? In this picture, our universe might be just one of an infinite ensemble, a single bubble floating in a cosmic foam of other universes, each with its own laws, constants, and dimensions. This naturally leads to the idea of the multiverse, where creation is not a one-time event, but an ongoing process of quantum blossoming. Still, the quantum fluctuation idea doesn't answer everything. It doesn't tell us why the quantum vacuum itself exists or where the laws of physics that govern it come from. It shifts the question of origins from why is there something rather than nothing to why is there a quantum vacuum at all? But even so, it represents a profound step forward. It replaces the notion of a supernatural beginning with a natural, testable framework rooted in known physics, one where the universe is not an anomaly, but an inevitable expression of the quantum fabric of reality.
If the quantum fluctuation hypothesis is correct, then we are the descendants of a spontaneous moment of uncertainty, a random fluctuation that didn't fade away. Our galaxies, our stars, even our consciousness itself, all trace back to a whisper in the vacuum, a tiny tremor that echoed across eternity. Yet, to truly grasp what this vacuum means, we must go deeper still, because the quantum vacuum is not an empty void. It is a dynamic, ever-changing entity, humming with latent energy. Understanding what it really is and how it might give rise to universes is the next step in unraveling the mystery of what came before the Big Bang. The word vacuum often evokes a sense of emptiness, a perfect void where nothing exists, a cosmic blank slate waiting to be filled. But in the context of quantum physics, the vacuum is anything but empty. The quantum vacuum is a seething, dynamic field of energy, alive with potential and fluctuation. It is the underlying fabric of reality itself, a medium in which particles spontaneously appear and disappear, where energy ebbs and flows in unpredictable ways, and where the distinction between something and nothing becomes blurred. Far from being a barren nothingness, it is a womb of all possibilities, a stage on which the universe itself might have originated. In quantum field theory, every type of particle corresponds to a field that permeates all of space. Even in the absence of particles, these fields are never completely still. They possess a zero-point energy, the lowest possible energy that cannot be removed. This zero-point energy manifests as tiny transient fluctuations that can momentarily produce particle-antiparticle pairs. These virtual particles appear out of the vacuum, interact briefly, and then annihilate, leaving no trace. A ceaseless dance of creation and destruction that has been confirmed experimentally through phenomena such as the Casimir effect and Hawking radiation near black holes. In this sense, the vacuum is not an absence of existence, but an arena brimming with activity, even if that activity is invisible and fleeting. This understanding reframes our notions of before the Big Bang. When physicists talk about the universe emerging from nothing, they are often referring to this quantum vacuum rather than a literal void. The vacuum could have existed timelessly, governed by the laws of quantum mechanics, waiting to give rise to a universe. In this view, the Big Bang was not creation ex nihilo in the traditional sense, but rather the transformation of a pre-existing quantum state into a self-sustaining cosmos. The quantum vacuum provides the seed, the fertile ground from which space-time, matter, and energy could emerge. The vacuum's ability to spawn particles spontaneously means that even a perfectly empty region of space is inherently unstable. Tiny fluctuations can amplify under certain conditions, potentially creating macroscopic structures, or, in the case of the universe, an entire space-time. This is the foundation of the quantum fluctuation hypothesis we discussed previously, where a small disturbance in the vacuum could inflate into a universe. In other words, the universe might not have been a unique miracle, but a natural consequence of the properties of the quantum vacuum. One of the most remarkable aspects of the quantum vacuum is that it allows for energy conservation at a cosmic scale, even during spontaneous creation. Positive energy, in the form of matter and radiation, can be exactly balanced by negative energy associated with gravitational attraction. This balance means that the emergence of a universe from the vacuum does not violate physical laws. The net energy remains zero. It's as if the vacuum can produce something from itself without requiring an external cause, simply because its own structure allows it. Moreover, the vacuum might not be static. It could contain multiple potential energy states, some more stable than others. A high-energy fluctuation could trigger a phase transition, releasing energy and expanding exponentially, a process that aligns closely with the theory of cosmic inflation. In this sense, the quantum vacuum is not just a passive stage. It is an active participant in the creation of universes, a dynamic medium capable of producing vast, structured cosmos from its own restless energy. Interestingly, this conception also opens the door to the multiverse idea. If the quantum vacuum is a pervasive, eternal field capable of producing universes, it may give rise to not one universe, but countless others. Each fluctuation could spawn a separate bubble universe with its own laws, constants, and dimensions. Our observable universe might then be just one of innumerable cosmic offspring, born from the same underlying quantum sea. The vacuum in this sense is both timeless and generative, capable of sustaining an endless cascade of creation. Yet the quantum vacuum is deeply mysterious. Despite its central role in modern physics, we are still far from understanding its full nature. What exactly is this sea of energy? Why does it exist at all? Why does it obey the laws of quantum mechanics, and could it exist without those laws? These are questions that edge into the philosophical as well as the scientific, reminding us that even the most rigorous theories have boundaries. Nevertheless, the quantum vacuum gives us a tantalizing glimpse into what might have preceded the Big Bang. It suggests that even if time itself began with the expansion of the universe, a pre-existing, timeless state, this restless, energetic vacuum, could have provided the conditions for creation. It's a realm where the ordinary concepts of before and after, existence and non-existence are no longer adequate. Here, the universe might emerge spontaneously, naturally, and repeatedly without an external cause from the inherent properties of reality itself. From the quantum vacuum, we can see the beginnings of new possibilities, a universe born from uncertainty, shaped by fluctuations and guided by the laws of quantum mechanics. But quantum fluctuations are not the only imaginative avenues scientists have explored. Some theorists have proposed models in which the universe doesn't emerge from a vacuum at all, but from an earlier phase of existence, or even from a cycle of expansions and contractions. This brings us to one of the most captivating ideas in cosmology, cyclic universe theories, where the cosmos may have existed eternally, undergoing endless transformations long before our own Big Bang.
The idea of a cyclic universe is both ancient and modern, a concept that has roots in early philosophical speculation and has evolved into one of the most intriguing frameworks in contemporary cosmology. The basic premise is elegant in its simplicity. The universe might not have had a single beginning, but instead could undergo endless cycles of expansion and contraction, with each Big Bang giving birth to a new cosmos, and each cosmic collapse, a big crunch, setting the stage for the next. In this model, the universe isn't a one-time creation event, but part of an eternal rhythm, an infinite cosmic heartbeat where death and rebirth are intertwined. One of the motivations for cyclic models is their ability to address some of the questions left unresolved by a singular Big Bang. For example, why is the universe so uniform on large scales? Why do the laws of physics and fundamental constants appear so finely tuned? In a cyclic scenario, each iteration of the universe could reset certain properties, smoothing out irregularities over vast timescales. Quantum fluctuations and thermodynamic processes could influence the nature of each new cycle, producing a universe that evolves and regenerates, maintaining its overall structure while allowing subtle variations. In modern physics, cyclic cosmology has taken several concrete forms. One early attempt was proposed by Richard Tolman in the 1930s. Tolman considered a universe dominated by matter and radiation, and calculated that in each cycle of expansion and contraction, entropy would increase. This presented a problem. If entropy accumulates with each cycle, then subsequent cycles would be longer and larger, and ultimately the universe would not be truly eternal in its previous form. While Tolman's original model highlighted the challenges of perpetual cycles, it laid the groundwork for more sophisticated approaches that could avoid this entropy buildup. Enter modern cyclic models, which draw from ideas in string theory, brain cosmology, and quantum gravity. In some scenarios, entropy produced in one cycle can be dissipated through mechanisms involving extra dimensions, or through interactions with a larger cosmological environment. One of the most well-known versions is the expyrotic universe, developed by Paul Steinhardt and Neil Turok in the early 2000s. In this model, our universe is a three-dimensional brain floating in a higher dimensional space. Collisions between brains trigger the equivalent of a Big Bang, initiating a new cycle of expansion. Between collisions, the universe contracts and smooths out, preparing the conditions for the next iteration. This approach elegantly avoids some of the entropy problems that plagued earlier cyclic models, and ties cosmology to cutting-edge theoretical physics. Another compelling feature of cyclic models is how they conceptualize time. In a single Big Bang scenario, time has a clear starting point. But in a cyclic universe, time is effectively eternal, stretching backward and forward across an infinite series of expansions and contractions. There is no absolute beginning or end. The universe simply exists as a sequence of cycles, each one giving rise to the next. This framework challenges our conventional ideas of causality, suggesting that what we perceive as the beginning, the Big Bang we observe, might simply be one phase in an eternal process. Cyclic models also intersect intriguingly with quantum mechanics. During the contraction phase of each cycle, quantum effects may dominate the behavior of spacetime at extremely high densities, smoothing out irregularities and seeding fluctuations that grow into large-scale structures in the next expansion. In this way, quantum mechanics doesn't just govern the tiniest scales, it actively shapes the evolution of the entire cosmos across cycles, embedding randomness, uncertainty, and probabilistic outcomes into the fabric of successive universes. Yet, cyclic cosmology is not without challenges. Observationally, it is difficult to test. How can we detect evidence of a universe that existed before ours if all information from prior cycles has been erased or hidden behind the veil of a new Big Bang? Some theorists have proposed subtle imprints, such as patterns in the cosmic microwave background or gravitational wave signatures that can hint at prior cycles. But these remain speculative. Moreover, the physics of the bounce, the transition from contraction to expansion, is not fully understood. It likely requires a theory that unifies general relativity and quantum mechanics, since classical gravity alone cannot prevent a singularity from forming during collapse. Yet, despite these hurdles, cyclic models offer a profoundly different perspective on cosmic origins. Rather than a singular creation event, they suggest a universe that is self-renewing, resilient, and eternal in a sense that stretches human imagination. Each cycle contains both death and rebirth. The collapse of one universe is not an end, but the prelude to the next. In this light, the Big Bang that we observe is not the ultimate beginning, but merely a rebirth, a new chapter in a story that may have no beginning and no final conclusion.
In exploring cyclic cosmology, we are invited to rethink the nature of existence itself. The universe may not be a one-off miracle, but part of a grand eternal rhythm, a cosmic heartbeat pulsing through the fabric of space-time. And while we may never directly witness prior cycles, the possibility that our universe is just one iteration among infinite others expands our sense of scale, possibility, and wonder. It is a vision of the cosmos where creation and destruction are not opposites, but partners in an endless dance, forever spinning the universe into new forms. This idea naturally leads to another refinement in modern cosmology, the Big Bounce models, which seek to describe not just cycles in general, but the precise mechanism by which a previous universe might collapse and rebound into the one we inhabit today. The concept of the Big Bounce takes the cyclic universe idea and gives it a more concrete, physically plausible framework. Instead of imagining an eternal series of expansions and contractions with vague transitions, the Big Bounce proposes a specific mechanism. The universe doesn't begin from a singularity, an infinitely dense point, but rather rebounds from the collapse of a prior universe. In this model, the Big Bang we observe is not the ultimate beginning of time and space, but a kind of cosmic reset, a dramatic bounce that converts contraction into expansion. This approach elegantly avoids the problem of singularities, predicted by classical general relativity, replacing an infinitely small and dense origin with a physically meaningful event governed by the laws of quantum gravity. The idea arises from the recognition that the classical equations of general relativity, while successful at describing large-scale cosmic dynamics, break down under extreme conditions. Near a singularity, density, temperature, and curvature theoretically become infinite, indicating that the theory is incomplete. The Big Bounce scenario addresses this by incorporating quantum corrections to gravity, which become dominant when the universe is at its smallest scales. These quantum effects can prevent total collapse, creating a repulsive force at ultra-high densities that causes the universe to rebound instead of collapsing into an inescapable singularity. In essence, the Big Bounce replaces the idea of creation from nothing, with a transition from one phase of the cosmos to another, governed by fundamental physics rather than metaphysical speculation. One of the most compelling frameworks for the Big Bounce comes from loop quantum cosmology, an application of loop quantum gravity to the entire universe. LQC suggests that space is not continuous, but composed of discrete quantized units. When a collapsing universe reaches a critical density, the quantum geometry creates a repulsive effect strong enough to halt the collapse and trigger a rebound. This means that the universe has a minimum size. It can never shrink to zero, and thus avoids the problematic infinities of the classical singularity. From this minimum, expansion begins anew, and what we perceive as the Big Bang is simply the outward phase of this cosmic cycle. Mathematically, the Big Bounce is modeled as a smooth transition rather than an abrupt explosion. The energy and matter from the previous contracting universe are carried over into the new expanding phase, potentially explaining certain observed properties of our cosmos, such as its homogeneity and flatness. Quantum fluctuations in the contracting phase can also be stretched and amplified during the bounce, seeding the structure of the universe we observe today, including the galaxies, stars, and cosmic web. In this sense, the history of the universe may be far richer than a single creation event. It could carry the imprints of a cosmos that existed long before the moment we traditionally call the Big Bang. Another fascinating implication of the Big Bounce is that it provides a potential resolution to the before problem. In a classical Big Bang, time itself begins at the singularity, making the question of what came before meaningless. But in the Big Bounce, time extends beyond the bounce itself. The prior universe existed in the past, collapsed, and then transitioned into our current universe. Time doesn't start at the Big Bang, it continues through the contraction and rebound, giving a coherent temporal framework that stretches backwards indefinitely. This perspective allows for a universe that is effectively eternal, though undergoing radical transformations across cosmic cycles. Physicists also explore variations of the Big Bounce in the context of higher dimensional theories, such as string cosmology.
In some string-inspired models, our universe exists as a three-dimensional brain moving through higher dimensional space. A previous universe may have collapsed, causing brains to collide or interact in ways that triggered a rebound, creating conditions for a new expansion. This mechanism not only aligns with quantum gravity ideas, but also opens the door to a multiverse scenario, in which multiple bounces might occur independently in different regions of a higher dimensional space. One of the appealing aspects of the Big Bounce cosmology is that it makes concrete predictions that could, in principle, be tested. For example, the cosmic microwave radiation, the faint afterglow of the early universe, might retain subtle imprints from the previous contracting phase. Tiny deviations in temperature or polarization patterns could hint at a pre-Big Bang history, offering a potential observational window into the universe that existed before our own. While current measurements are not yet conclusive, future high-precision observations could provide evidence supporting or falsifying the Big Bounce scenario. Conceptually, the Big Bounce offers a radical shift in perspective. Instead of imagining the universe emerging from an abstract singularity, it suggests a cosmic continuity, where birth and rebirth are part of a dynamic process. Each cycle could leave a faint legacy in the subsequent universe, creating a kind of cosmic memory encoded in spacetime itself. The universe is no longer a singular miracle or a one-off creation event. It is part of a chain of transitions, each linked to the next by the laws of physics. Yet, like all cutting-edge cosmology, the Big Bounce raises deep questions. What were the properties of the previous universe? Could the physical constants or laws differ from one cycle to another? And how many bounces might have occurred before ours? These questions stretch our imagination and challenge the limits of observation, pushing us to think about time, causality, and existence in ways far removed from everyday experience.
In many ways, the Big Bounce bridges the gap between classical physics and quantum uncertainty. It respects the continuity and geometry of space-time described by Einstein, while incorporating the probabilistic and discrete nature of quantum mechanics. By doing so, it provides a physically plausible mechanism for a universe without a singular beginning. A universe where the Big Bang is not a point of creation ex nihilo, but the dramatic expansion phase of a long cosmic cycle. From the Big Bounce, our attention naturally turns outward again, beyond a single rebounding universe to the possibility that multiple universes might exist simultaneously. This brings us to the concept of the multiverse, where our cosmos is just one bubble in a vast, potentially infinite cosmic landscape. The idea of the multiverse stretches our imagination to its outermost limits. While the Big Bang and Big Bounce theories focus on the origin and evolution of our universe, the multiverse concept asks an even bolder question. What if our universe is not unique? What if the cosmos we inhabit is just one bubble in a vast, possibly infinite sea of universes, each with its own laws, constants, and dimensions? The multiverse challenges the notion of a single cosmic stage, and instead presents a sprawling cosmic foam, a reality composed of countless universes coexisting, perhaps forever, in an overarching framework beyond our direct perception. The idea has roots in both philosophy and physics. Philosophically, it resonates with ancient speculation about multiple worlds from the atomists in ancient Greece to the infinite worlds proposed in Eastern metaphysics. Physically, it arises naturally from several lines of modern theoretical research, particularly cosmic inflation, quantum mechanics, and string theory. In the context of inflation, the multiverse emerges as a natural consequence of how space itself expands. During the earliest moments of our universe, space underwent an extraordinarily rapid growth, a phase known as inflation, which magnified tiny regions of quantum fluctuations to enormous scales. In many models, this inflation does not end uniformly everywhere. Some regions stop inflating and form discrete pocket universes like ours, while other regions continue inflating indefinitely, producing new universes in an ending fractal-like process. This picture of the cosmos is sometimes called eternal inflation.
In this framework, each pocket universe is like a bubble forming within a vast inflating space. Each bubble has its own properties. It may have different physical constants, different numbers of dimensions, or even different types of particles. Our universe is simply one of the bubbles where the conditions happen to favor life, stars, planets, and life. Beyond our observable horizon, countless other bubbles could exist, potentially forever expanding, colliding, or remaining isolated in the grand cosmic foam. Quantum mechanics further reinforces this idea. The universe at its origin is governed by probabilistic laws. Tiny fluctuations in energy and density could lead to vastly different outcomes in different regions of inflating space. Some fluctuations might produce universes with physical constants that prevent star formation. Others might create universes that expand forever or collapse rapidly. The multiverse naturally accommodates these variations, providing a framework in which every physically possible outcome might actually occur somewhere. In this sense, our universe may be the one where conditions happen to favor life, but countless others might be entirely inhospitable, with laws of physics that seem alien or nonsensical from our perspective. The multiverse concept also offers intriguing explanations for some of the apparent fine-tuning in our universe. Physical constants such as the strength of gravity, the mass of the electron, or the cosmological constant appear precisely tuned to allow for the existence of galaxies, stars, and life. In a multiverse scenario, this fine-tuning is not surprising. Among countless universes with varying parameters, some are bound to have the conditions necessary for life, and we naturally find ourselves in one of those rare universes. This perspective transforms what once seemed like a profound cosmic coincidence into a statistical inevitability. While the multiverse is a breathtaking and conceptually liberating idea, it also raises profound challenges. By definition, most of the other universes in the multiverse are beyond our observational reach, separated from us by inflating space or different dimensions. This raises questions about whether the multiverse is scientifically testable, or whether it remains a speculative framework. Nonetheless, cosmologists are exploring indirect ways to detect multiverse signatures. For instance, collisions between bubble universes in the early inflationary epoch could leave subtle imprints in the cosmic microwave background, tiny anomalies in the large-scale structure of our universe, or unexplained gravitational wave patterns. These potential fingerprints provide hope that the multiverse might one day move from theoretical abstraction to empirical science. Beyond physics, the multiverse profoundly alters our philosophical perspective. If our universe is just one bubble among countless others, notions of uniqueness and centrality are challenged. Life, existence, and even the very laws of nature may not be special. They may simply reflect the random conditions of our particular bubble. At the same time, the multiverse offers a breathtaking vision of reality, a cosmos of immense diversity, in which every possible universe is realized somewhere in the infinite expanse of existence. This idea naturally transitions to the next layer of understanding, eternal inflation, which provides the dynamic mechanism by which these countless universes, these bubbles, are continually created, whereas the multiverse describes the static ensemble of possible universes. Eternal inflation explains how they come into being and why the process never truly stops.
Eternal inflation is an extension of the inflationary model of the universe that takes the already mind-bending concept of cosmic inflation to an almost incomprehensible scale. In the standard inflationary theory, the universe underwent an extremely rapid expansion in the first fractions of a second after the Big Bang, stretching space by enormous factors and smoothing out any irregularities. This inflationary period explains why the universe appears so homogeneous and isotropic on large scales, and it provides the seeds for the cosmic structures we see today, from galaxies to clusters of galaxies. Eternal inflation takes this idea further, proposing that inflation never completely stops. While pockets of space, like our observable universe, exit the inflationary phase and form bubble universes, the background space outside these bubbles continues to expand exponentially, ensuring that new bubbles are constantly being created. This leads to a picture of a multiverse in dynamic motion, a a cosmic foam of continuously forming universes, each bubble representing a separate space-time region where inflation has ended and familiar physics can take hold. Outside these bubbles, the inflationary field, sometimes called the inflaton field, remains high in energy, driving expansion at an exponential rate. Even as one region of space ceases inflating and becomes a universe, other regions continue to inflate, and new universes spontaneously emerge. In this framework, the creation of universes is not a one-time event, but an ongoing process that can, in principle, continue indefinitely. One of the fascinating aspects of eternal inflation is the way it reconciles the quantum and the cosmic. Quantum fluctuations in the inflaton field play a crucial role. In some regions, the field's energy drops low enough to end inflation locally, forming a bubble universe. In other regions, fluctuations maintain the energy high, allowing inflation to continue. These fluctuations mean that the fate of a region of space is probabilistic. Some areas stop inflating, while others persist, creating a fractal-like structure of inflating and post-inflationary regions. Because of this randomness, no matter how many universes form, there is always more inflating space in which new bubbles can emerge, making the process eternal. Eternal inflation also addresses the question of initial conditions. One of the puzzles of cosmology is why our universe seems so fine-tuned for life. Eternal inflation provides a statistical explanation. Countless universes form, each with different properties. Some bubbles might have physical constants that prevent stars or galaxies from forming. Others might collapse immediately or expand in bizarre ways. Only a tiny fraction will have the precise combination of constants that allows complex structures and life to develop. We happen to inhabit one of those bubbles, not because our universe is uniquely special, but because observers can only exist in universes where conditions permit their existence, a reasoning aligned with the anthropic principle. Eternal inflation also has implications for the concept of time and the structure of reality itself. In the inflating background, time effectively extends infinitely into the future. New universes can form endlessly, each with its own local arrow of time. The global picture of reality becomes vastly larger and more complex than any single universe can capture. In a sense, the universe becomes almost a meaningless term. What we call the universe is merely a single bubble in a vast and ever-expanding multiverse. Furthermore, eternal inflation can accommodate extreme diversity among universes. Depending on the specifics of the inflaton field and its potential energy landscape, different bubble universes could feature variations in spatial dimensions, fundamental forces, particle types, or even the nature of time itself. This suggests a cosmos so varied that every logically possible universe might exist somewhere, forming a supremely vast ensemble of realities. In this sense, eternal inflation and the multiverse concept complement each other. The multiverse describes the collection of all possible universes, while eternal inflation describes the mechanism by which they continuously come into existence. There are, however, conceptual and practical challenges. Observing other universes directly is beyond our current technological capabilities. They are separated from us by inflating space that expands faster than light, making causal contact impossible. This raises profound philosophical questions about what it means for something to be real if it cannot be observed. Nonetheless, cosmologists hope that subtle imprints from the inflationary process might provide indirect evidence. For instance, tiny anomalies in the cosmic microwave background or patterns in the distribution of galaxies that hint at interactions with neighboring bubble universes. Eternal inflation also reshapes how we think about beginnings. In a simple Big Bang scenario, time starts at a single moment. But in eternal inflation, the process itself may have no true beginning. Even if a local universe has a finite age, the inflating background could extend infinitely into the past, creating an eternal self-generating structure. This idea dovetails intriguingly with some interpretations of quantum cosmology, where time and space are emergent properties rather than fundamental absolutes, and the very notion of a singular origin is replaced with a self-perpetuating cosmic process. This leads naturally to a consideration of how fundamental physics, especially ideas like string theory and higher dimensional brains, might provide the backdrop for eternal inflation. If inflation and universe creation are embedded in a higher dimensional space, collisions between brains or the dynamics of extra dimensions could provide additional mechanisms for generating new universes, further expanding the potential scale and diversity of the multiverse. In this way, eternal inflation is not just a theory about rapid expansion. It is a doorway into a broader cosmological framework, where universes, dimensions, and even the laws of physics themselves are part of a vast, evolving landscape. The notion of eternal inflation, then, transforms our understanding of reality from a single, bounded universe into an ever-growing dynamic structure, where creation never truly ends. Each bubble universe is a transient region in an infinite, inflating backdrop, a fleeting oasis in a vast quantum sea, continuously giving rise to new realms of existence. From this perspective, our observable universe is not the whole story. It is merely one expression of an eternal, generative process, a single spark in a limitless, unfolding cosmic fire. From eternal inflation, we naturally transition to the even more speculative but deeply fascinating frameworks proposed by string theory, where the universe might exist as a multidimensional brain, and cosmic collisions between such brains could trigger events like our Big Bang, connecting eternal inflation with the fundamental structure of reality itself. String theory introduces a radically different perspective on the nature of reality, one that stretches far beyond the familiar three dimensions of space and the single dimension of time. At its core, string theory proposes that the fundamental constituents of the universe are not point-like particles, as described by the standard model of particle physics, but tiny, vibrating strings of energy. The way these strings vibrate determines the properties of particles, such as mass, charge, and spin. But perhaps even more remarkably, string theory requires additional spatial dimensions beyond the three we experience. Depending on the version of the theory, there may be as many as 10 or 11 dimensions, with most of them compactified into scales so small they are imperceptible to us. Within this multidimensional framework, our familiar universe could exist as a three-dimensional brain, a membrane-like structure embedded in a higher dimensional space, often referred to as the bulk. Everything we observe, including matter, radiation, and the forces of the standard model, would be confined to this brain. Gravity, however, is unique in this context. It can propagate into the extra dimensions, which may help explain why gravity is so much weaker compared to other fundamental forces. This higher dimensional picture transforms the way we think about cosmology. Our universe may just be one brain among countless others, floating in a multidimensional bulk like a soap bubble drifting in a vast, unseen ocean. One of the most compelling aspects of brain cosmology is its potential explanation for the Big Bang. According to some models, our universe's birth was not the creation of all space and time from a singularity, but the result of a collision between brains. Imagine two three-dimensional brains moving through the higher dimensional bulk. When they collide, the enormous energy released could heat the brains to extreme temperatures, create matter, radiation, and trigger the rapid expansion we recognize as the Big Bang. In this scenario, the Big Bang is not a singular point in time, but a cosmic event caused by the interaction of pre-existing structures in higher dimensions. Space and time, as we experience them, emerge on the brains after the collision, giving rise to a new universe capable of supporting stars, galaxies, and life. This approach offers a natural mechanism for some of the puzzling features of our universe. For instance, the collision could explain why the early universe was so hot and dense, why it began expanding so rapidly, and why it exhibits a high degree of uniformity and flatness. The properties of the brains and the dynamics of their interaction could also influence the physical constants and the fundamental forces observed in our universe, offering a potential explanation for the apparent fine-tuning necessary for life. In other words, the very structure of our cosmos might reflect the characteristics of the higher dimensional brains from which it emerged. String theory and brain collisions also connect intriguingly with other cosmological concepts we've discussed, such as eternal inflation and the multiverse. In some models, multiple brains exist in the bulk, each capable of generating its own universe through collisions or fluctuations. These universes might differ dramatically from one another, with varying physical constants, particle types, or even numbers of dimensions. The multiverse in this picture is not just a statistical consequence of eternal inflation, but a natural outcome of the geometry and dynamics of higher dimensional space. Collisions between brains could continuously spawn new universes, each with its own laws of physics and its own history, forming a vast, dynamic ensemble beyond our direct observation. One of the fascinating implications of brain cosmology is that the early universe may retain subtle imprints of these higher dimensional interactions. The cosmic microwave background, the faint afterglow of the Big Bang, could contain anomalies or patterns that reflect the geometry of the brains or the energy released during collisions. Gravitational waves, ripples in the fabric of spacetime, might also carry signatures of brain interactions, potentially providing a window into dimensions beyond our own. Detecting such evidence would not only confirm aspects of string theory, but also provide a tangible connection to events that occurred in the higher dimensional bulk before the birth of our universe. String theory also raises profound philosophical and scientific questions about the nature of reality. If our universe is a brain among many, then existence may be far larger and more complex than we can observe. Universes could collide, merge, or exist independently, each governed by its own set of physical laws. The very notion of a beginning becomes fluid. Our Big Bang might be the latest in a potentially infinite series of collisions, a single event in an ongoing, multi-dimensional cosmological process. Time, space, and causality as we know them might be local properties of our brain, not fundamental aspects of the entire bulk. Moreover, the brain picture provides a compelling bridge between quantum physics and cosmology. Collisions and fluctuations at the brain level are inherently quantum mechanical processes, yet they give rise to classical, large-scale structures like galaxies and clusters of galaxies. This framework thus unites the probabilistic, indeterminate world of quantum mechanics with the smooth, deterministic expansion of spacetime described by general relativity, a reconciliation that is central to our understanding of the early universe. In essence, string theory and brain cosmology allow us to imagine the Big Bang not as a mysterious singular moment of creation ex nihilo, but as a physical event embedded in a higher dimensional reality, governed by the same laws of physics that underpin all matter and energy. The universe we inhabit may be one of many brains, each a dynamic, evolving structure within an infinite, multi-dimensional bulk. Our existence, our stars, and even our laws of physics could be shaped by collisions and interactions that occurred before the concept of time as we know it even existed. This perspective naturally transitions into the groundbreaking work of Stephen Hawking and others, who propose that the universe might not require a boundary or initial singularity at all. Instead of a collision triggering a start, what if the universe is boundaryless, like the surface of a sphere, curving smoothly in time so that questions about before the Big Bang become meaningless? This leads directly into the Hawking no-boundary proposal, a radical rethinking of the very origin of the cosmos. The Hawking no-boundary proposal offers one of the most profound and mind-stretching ideas about the origin of the universe, challenging our very notions of time and causality. Traditionally, cosmologists have asked what existed before the Big Bang, as if time were an eternal backdrop against which events unfold. But Hawking suggested that time itself might have a beginning. Not in the sense of a singular instant of creation, but in the sense that time is finite, yet has no boundary, much like the surface of a sphere. On the surface of a sphere, there is no edge. You can travel in any direction indefinitely without ever encountering a boundary. And yet the surface has a well-defined finite area. Hawking proposed that the universe could behave similarly. Time and space curve in such a way that the universe has a smooth, self-contained beginning, with no singular edge or before to speak of.
In technical terms, Hawking used Euclidean quantum gravity to describe this idea, employing imaginary time to smooth out the singularity and create a finite yet unbounded spacetime geometry. One of the most compelling features of the no-boundary proposal is its elegance and simplicity. It removes the need for a universe to emerge from nothing in a violent or inexplicable act. Instead, the universe naturally arises from the laws of physics themselves. The initial conditions that produce a cosmos like ours are not arbitrarily imposed. They are intrinsic to the geometry of spacetime and the quantum rules governing the early universe. In other words, the universe doesn't require a cause outside of itself. Its smooth, rounded structure ensures that it can emerge spontaneously in accordance with physical laws.
Hawking's approach also connects beautifully with quantum mechanics. By describing the universe in terms of a wave function, the no-boundary proposal treats the cosmos as a quantum system. The wave function encodes all possible histories of the universe, including the different ways it could have expanded, cooled, and formed structures like galaxies, stars, and planets. In this sense, our observable universe is just one realization of the full spectrum of possibilities allowed by the quantum wave function. The no-boundary condition selects the histories that are most probable, favoring universes that are large, smooth, and capable of forming complex structures. This explains why our universe appears homogeneous and isotropic on large scales, without requiring finely tuned initial conditions. A striking implication of this idea is that time emerges gradually from a quantum-dominated state. Near what we would call the beginning, the distinction between space and time is blurred. Space itself may have existed in a highly curved, four-dimensional configuration, with time behaving more like another spatial dimension. Only as the universe expands and cools does time take on the familiar arrow we experience, flowing from past to future, marked by entropy increase and causality. The no-boundary proposal provides a smooth bridge from a timeless, quantum-dominated early universe to the classical cosmos we observe today. This proposal also complements and extends other cosmological models, such as inflation and quantum cosmology. Whereas inflation explains the rapid expansion and uniformity of the universe, the no-boundary condition explains why inflation itself could occur naturally. It provides a framework in which the universe is self-contained, needing no external agent or singular origin. The birth of the cosmos is not a creation event in the traditional sense, but a natural, probabilistic outcome of the quantum geometry of spacetime. Philosophically, the Hawking no-boundary proposal reshapes our understanding of beginnings. If time itself is finite but unbounded, then the question of ultimate origin becomes irrelevant. There is no before in the conventional sense. The universe is like a closed surface that is self-contained, with no edge or starting point to define a cause. In this light, the cosmos is both eternal and finite, existing without a temporal boundary, yet remaining comprehensible within the laws of physics. It is a vision of reality where creation is embedded within the universe's own geometry rather than imposed from outside. The no-boundary proposal also raises fascinating implications for the multiverse and cosmology at large. If the universe emerges as a wave function with many possible histories, then multiple universes could naturally exist as alternative realizations of the same underlying quantum geometry. Each bubble universe might follow different histories, with its own laws, dimensions, and constants. In this sense, our no-boundary proposal not only provides a smooth beginning for our universe, but it also offers a framework for understanding why many possible universes could exist, seamlessly connecting with ideas like the multiverse and eternal inflation. Finally, the Hawking no-boundary model reinforces a profound philosophical insight. Beginnings may not be violent, abrupt, or singular. The universe need not emerge from a first moment in time, nor require an external cause. Instead, existence can emerge naturally, embedded in the intrinsic curvature and quantum rules of spacetime itself.
Time, space, and matter flow from this rounded, self-contained geometry, giving rise to the cosmos we inhabit without invoking paradox or mystery. It is a vision of reality that is both deeply elegant and humbling, reminding us that the universe is far more subtle, intricate, and beautiful than our everyday intuition allows. With this understanding, we are naturally led to explore loop quantum cosmology, a framework that also seeks to resolve the singularity problem by applying quantum gravity to the universe's earliest moments. While Hawking's proposal smooths the beginning geometrically, loop quantum cosmology introduces a quantum bounce, preventing infinite densities and providing yet another lens through which to understand what may have preceded the Big Bang. Loop quantum cosmology provides one of the most mathematically rigorous and conceptually intriguing ways to rethink the very beginning of the universe. It is an application of loop quantum gravity, a theory that seeks to quantize spacetime itself, to the entire cosmos. While classical general relativity predicts that the universe originated from a singularity, an infinitely dense and hot point where the laws of physics break down, LQC replaces this singularity with a quantum bounce. In this framework, the extreme density and curvature near the beginning of the universe do not produce infinities. Instead, quantum geometric effects create a repulsive force at extremely small scales, halting the collapse and causing the universe to rebound, expanding into the cosmos we observe today.
The foundational idea behind loop quantum gravity is that spacetime is not continuous, as classical physics assumes, but discrete. It is composed of tiny, quantized loops of geometry, forming a kind of cosmic fabric that has a minimum scale, often referred to as the Planck length. At everyday scales, this discreteness is imperceptible, and spacetime appears smooth. However, at extremely high densities, such as those encountered in the early universe, the discrete nature of spacetime becomes crucial. The loops resist compression, producing a quantum pressure that prevents the formation of a singularity. This is the mechanism behind the bounce. Instead of collapsing to zero volume, the universe reaches a minimum, finite size, and then begins to expand again. One of the remarkable aspects of LQC is that it allows time to extend through the bounce, effectively creating a pre-Big Bang phase. The universe that rebounded into our observable cosmos was preceded by a contracting universe. This pre-bounce universe could have had very different properties, and its collapse is what set the stage for our current expansion. In this sense, LQC provides a natural answer to the before problem. The universe has a history that predates what we traditionally call the Big Bang, yet there is no singular starting point where physics fails. Time is continuous through the bounce, and the laws of physics remain valid across the transition. This framework has several important implications. For one, it provides a natural mechanism for resolving cosmological singularities. The classical Big Bang singularity is replaced by a deterministic quantum process, meaning that the early universe is not a chaotic, undefined state, but a predictable outcome of the dynamics of quantum spacetime. This also addresses issues related to fine-tuning and initial conditions. The contracting phase prior to the bounce could imprint subtle features on the post-bounce universe, influencing its large-scale structure, the distribution of matter, and even the seeds of cosmic inflation. In essence, the pre-Big Bang universe is not erased. It contributes to the properties of our cosmos. Loop quantum cosmology also dovetails with ideas of cyclical and bouncing universes. While LQC does not inherently require infinite cycles, it naturally accommodates them. The bounce mechanism can repeat, with the universe undergoing sequences of contraction and expansion, each governed by quantum gravitational effects. This creates a vision of a universe that is eternal in time, though undergoing profound transformations between phases of contraction and expansion. In this framework, the Big Bang is not the ultimate origin, but a transitional event, a bounce between two macroscopic states of the cosmos. The mathematics of LQC also leads to testable predictions. For instance, quantum gravitational effects near the bounce could leave observable imprints in the cosmic microwave background, or in the distribution of primordial gravitational waves. These signatures might allow physicists to distinguish LQC from classical inflationary models or from other quantum cosmology proposals.
Detecting such signals would provide not only evidence for a quantum bounce, but also a window into physics at energy scales far beyond the reach of any particle accelerator. Conceptually, LQC shifts the philosophical framing of the universe's beginning. The idea that the cosmos could emerge from a quantum bounce rather than from absolute nothingness suggests that creation is a natural, law-abiding process rather than a singular miracle. It reinforces the notion that the universe is fundamentally self-contained. Its existence, evolution, and rebirth are consequences of quantum geometric rules. The pre-Big Bang phase is as real as the post-Big Bang universe, and the cosmos is understood as a continuous, self-consistent entity rather than a phenomenon that begins from nothing. Furthermore, LQC highlights the interplay between quantum mechanics and general relativity. Where classical physics fails at extreme densities, quantum corrections intervene, providing a consistent framework for understanding the earliest moments of cosmic history. This is a rare achievement. It unites the two most successful but seemingly incompatible pillars of modern physics, offering a coherent picture of the universe across scales from the subatomic to the cosmic. LQC also invites us to rethink the nature of beginning and creation. If the universe can rebound from a prior contraction, then beginnings are not singular events, but transitions. Time is not an emergent property starting at a point, but a continuous thread stretching across bounces. The universe may exist eternally, yet with distinct phases of contraction and expansion, each with its own physical properties. This perspective aligns intriguingly with other approaches we've explored, such as the cyclical universe, the Big Bounce, and brane collisions, suggesting a convergence of ideas pointing toward a universe without an ultimate beginning in the classical sense.
The natural question then becomes, could the universe have always existed in some form, even before the bounce, perhaps in a static or slowly evolved state? This leads into emergent universe theories, where the cosmos exists eternally in a quasi-static phase before transitioning into the expanding universe we observe today. Unlike LQC, which emphasizes the bounce mechanism, emergent universe models focus on a universe that is stable and unchanging in its distant past, eventually evolving into expansion without requiring a singular origin. Emergent universe theories offer yet another fascinating perspective on cosmic origins, proposing a scenario that challenges the conventional notion of a singular beginning. Unlike the classical Big Bang or even loop quantum cosmology, which focus on a dramatic origin event, emergent universe models envision a cosmos that has existed forever in a quasi-static or slowly evolving state, before transitioning into the expanding universe we observe today. In this framework, the universe doesn't spring into existence from nothing, nor does it rebound from a prior contraction. Instead, it undergoes a gradual change of state, moving from a stable or nearly stable configuration into the dynamic, expanding cosmos familiar to us. This approach eliminates the need for an initial singularity or a first moment of time, offering a smooth, self-contained picture of existence. The basic idea is that in the very distant past, the universe could have been in an almost static condition, possibly with a finite but extremely large scale, where gravitational attraction was balanced by some form of exotic energy, such as a cosmological constant or a scalar field. In this state, the universe is eternal, no beginning, no end, and experiences negligible change over vast timescales. Small perturbations or instabilities in the static configuration eventually trigger a transition, causing the universe to begin expanding slowly at first, then accelerating into the rapid expansion phase we associate with inflation. The result is a cosmos that evolves naturally from a stable, timeless phase into a dynamic, evolving universe, without requiring a singular origin. Emergent universe models can resolve several conceptual challenges faced by traditional cosmology. For instance, they provide a way to avoid the singularity problem entirely, sidestepping the infinities of density and temperature that plague the classical Big Bang model. Since the universe existed in a stable or quasi-stable configuration for an indefinite past, there is no first moment or physical laws break down. This gives a cosmos a self-consistent past, extending indefinitely backward in time,
yet still allowing for the observed expansion, structure formation, and evolution of galaxies and stars. Physically, these models often rely on scalar fields, fields that permeate space and carry energy, or modifications to general relativity to maintain the initial static state and control the transition to expansion. The energy from these fields acts like a delicate balancing force, counteracting the gravitational pull of matter to prevent collapse. When the balance is slightly disturbed, perhaps by quantum fluctuations or instabilities in the field, the universe begins to expand slowly. Over time, this expansion accelerates and conventional cosmic evolution unfolds. In some formulations, the expansion eventually triggers a phase of inflation, further smoothing the universe and generating the density fluctuations that seed galaxies, much like in standard inflationary theory. Emergent universe theories also intersect with philosophical and conceptual questions about time and existence. If the universe existed eternally in a stable state, then the traditional question of what came before the Big Bang becomes irrelevant. There was no beginning, only a continuous state that eventually transitioned into expansion. Time in this sense is not created at a singular moment, but is a fundamental continuous feature of the cosmos. This challenges the notion that creation requires an initial cause or singularity, suggesting instead that the universe may be self-sufficient and eternal, with expansion as a natural phase change rather than a miraculous beginning. Several specific emergent universe models have been proposed in modern theoretical cosmology. Some rely on modifications of general relativity to include a bounce-free solution that maintains a quasi-static past. Others use scalar fields or other exotic forms of energy to achieve stability over infinite time while allowing for a gradual transition into expansion. Despite differences in technical details, all these models share the central idea that the universe did not begin at a finite point in time. It existed, essentially timelessly, before evolving into the cosmos we see today. One particularly appealing aspect of emergent universe models is that they offer conceptual continuity with other quantum and cosmological approaches we've explored. For example, in loop quantum cosmology, a quantum bounce replaces the singularity. In emergent universe theories, there is no singularity at all. The universe transitions smoothly from a static phase to expansion. Similarly, ideas from brane cosmology or eternal inflation could potentially be incorporated, where the initial quasi-static state is a local feature within a higher dimensional bulk or inflating background. These connections suggest that emergent universes may be part of a broader tapestry of models reconciling quantum mechanics, general relativity, and cosmology. Philosophically, the emergent universe challenges our intuitions about beginnings and nothingness. If the cosmos existed eternally in a stable state, the idea of a literal nothing prior to creation becomes irrelevant. There was no vacuum waiting to be filled, no external cause required. Instead, the universe is a self-sustaining system, capable of undergoing natural transitions and evolution entirely according to the laws of physics. This resonates with broader debates in cosmology and metaphysics, questioning whether true nothingness is even a meaningful concept. Ultimately, emergent universe theories invite us to rethink cosmic origins not as a singular event, but as a natural evolution of an eternal, self-contained cosmos. Expansion, structure, and the Big Bang itself are simply phases in a long, ongoing story, one that stretches infinitely into the past. This perspective provides a remarkable complement to the quantum, cyclical, and multiversal models we've discussed, highlighting the diversity of ways in which modern physics attempts to answer the age-old question, what was there before the Big Bang? From considering universes that exist eternally in a stable state, we are led naturally to the final contemplation of this journey, the question of nothingness itself, and what it truly means to say that the universe could have emerged from nothing. This philosophical and scientific puzzle pushes the boundaries of understanding, bridging physics, metaphysics, and the deepest human curiosity about existence. The question of nothing may be the most profound and unsettling in all of cosmology and philosophy. When we ask what existed before the Big Bang, we often assume that before the universe there was literally nothing. An absolute void devoid of space, time, matter, energy, or even the laws of physics. But is such a state even conceivable? Modern physics challenges our intuitive notion of nothingness, suggesting that what we think of as nothing may not truly be empty at all. In quantum mechanics, for instance, the vacuum is never truly void. It is a seething, fluctuating field of energy capable of spawning particles and even entire universes. In this sense, nothingness as absolute emptiness may be physically impossible, and every nothing we conceive of is already imbued with potential, a kind of latent something waiting to manifest. Philosophers have long debated the concept of nothingness. Classical thought often treated nothing as the absence of being, a complete negation of reality. But physics reframes the issue. Even in a vacuum devoid of matter, energy, or radiation, quantum fields persist, governed by immutable laws. Virtual particles pop in and out of existence constantly, illustrating that empty space is, paradoxically, never empty. From this perspective, the universe might arise not from a true void, but from a state that is empty only in a classical sense, while rich in quantum potential. Even the processes we've discussed, quantum fluctuations, the Big Bounce, emergent universes, or brain collisions, operate within pre-existing physical frameworks. They show that creation, in a scientific sense, does not require absolute nothingness. It requires only the possibility inherent in physical laws.
This debate also highlights a subtle but critical distinction. There is a difference between philosophical nothing and physical nothing. Philosophical nothing is the total absence of anything imaginable or conceivable. Physical nothing, as used in modern cosmology, may still include fields, laws, or vacuum energy. For example, in the quantum fluctuation hypothesis, universes can pop into existence from a vacuum state, but this vacuum is not nothing in the absolute sense. It is a physical state with properties and dynamics. Even the concept of empty space in general relativity is a structure. It has geometry and can curve, expand, or contract. In other words, the universe may never have truly emerged from nothing. It may have emerged from a pre-existing framework that itself obeys natural laws. Some theorists even suggest that absolute nothingness is logically impossible. If there were truly nothing, there would be no laws, no space, no time, no potential for existence, and therefore nothing could ever emerge. The fact that anything exists at all, the universe, the multiverse, space, time, energy, may imply that a form of something is fundamental, unavoidable, and eternal. In this view, nothingness is not the default state of reality. Existence itself may be the default state. This notion reframes our understanding of cosmic origins. Instead of asking why the universe exists rather than nothing, we might ask why the universe exists in this particular form, with these laws, constants, and structures. Moreover, the nothing debate connects with many of the cosmological models we've explored. In quantum cosmology and the no-boundary proposal, the universe arises naturally from a smooth, self-contained geometry. In loop quantum cosmology, it rebounds from a pre-existing quantum state. In emergent universe models, it exists eternally in a quasi-static phase before transitioning to expansion. Even multiverse and eternal inflation models operate within a background of laws and quantum fields. Nothing is never truly absolute. These ideas collectively suggest that the universe's origin may be less about creation from absolute nothingness and more about the unfolding of possibilities inherent in a pre-existing structure of reality. This debate also has profound philosophical implications. If nothingness is impossible, then existence itself may be necessary, a fundamental property of reality rather than a contingent outcome. It challenges human intuitions about beginnings, causality, and creation. We are forced to confront the possibility that the universe has always existed in some form, whether as a quantum vacuum, a higher dimensional brain collision, or an eternal emergent cosmos.
The question shifts from why is there something rather than nothing to why does existence manifest in this particular form, with these laws, constants, and structures? The nothing debate also encourages a sense of humility and wonder. Even with the most advanced theories of quantum cosmology, string theory, or brain dynamics, we are confronting concepts that stretch human comprehension, realities where time has no beginning, universes that emerge spontaneously from a quantum fluctuations, and fields that exist in a state richer than our ordinary notion of emptiness. In grappling with nothingness, we are really grappling with the very nature of reality itself, probing the boundary between physics, metaphysics, and imagination. Ultimately, thinking about nothingness invites us to reconsider the Big Bang, the multiverse, and all the preceding theories we have explored. Whether the universe emerged from a quantum vacuum, a higher dimensional brain collision, a pre-existing static phase, or a quantum bounce, every model implicitly acknowledges that absolute nothing may be impossible. What we perceive as the beginning is just a transition from one state of existence to another, a manifestation of the latent possibilities embedded in the fabric of reality. This realization bridges the gap between physics and philosophy, science and wonder, guiding us to a deeper understanding of both the universe and our own place within it. With this perspective, we arrive at the final reflection. Whatever came before the Big Bang, whether quantum fluctuations, brain collisions, eternal inflation, or a timeless static universe, remains one of the greatest mysteries of science, inspiring awe, curiosity, and a relentless quest to comprehend the origins of everything. It is a journey that reminds us that the cosmos is not merely a collection of matter and energy, but a profound tapestry of existence, possibility, and wonder.
As we draw this extraordinary journey to a close, it becomes clear that the question of what existed before the Big Bang is not merely a puzzle for physicists or philosophers, it is a profound invitation to marvel at the cosmos and at our own place within it. Every model we've explored, from quantum fluctuations to the multiverse, from loop quantum cosmology to emergent universes, offers a different lens through which to glimpse the origins of reality. Yet none provides a definitive answer. And perhaps that is part of the wonder. The universe resists easy explanations, reminding us of the vastness of what we have yet to understand. It challenges our assumptions about time, space, and nothingness, and pushes the boundaries of both imagination and scientific inquiry. The mystery of the universe's beginnings compels us to reflect not only on the cosmos itself, but on our own origins as conscious observers capable of asking such questions. When we contemplate the possibility of a pre-Big Bang state, whether it was a quantum vacuum teeming with potential, a prior contracting universe that rebounded, a three-dimensional brain colliding in higher dimensions, or a timeless emergent cosmos, we are confronting the very processes that eventually led to stars, planets, life, and ultimately ourselves. Every particle in our bodies, every atom that makes up our world can be traced back to the earliest phases of cosmic evolution. In seeking to understand what came before the Big Bang, we are, in essence, seeking to understand ourselves and the extraordinary journey of existence that brought us here. Perhaps the most humbling and exhilarating aspect of this exploration is that it reminds us how much remains unknown. Science has given us powerful tools, general relativity, quantum mechanics, string theory, cosmology, yet even these frameworks only hint at the true nature of the universe's origin. The edge of knowledge is a frontier where physics meets philosophy, where mathematics meets imagination, and where curiosity becomes a driving force for discovery. It is a place where every hypothesis, every calculation, and every observation deepens our appreciation for the universe's complexity and elegance, even when definitive answers remain elusive. Ultimately, the story of what may have existed before the Big Bang is a story of wonder. It invites us to embrace mystery, to ask questions that stretch beyond our ordinary experience,
and to marvel at the ingenuity of the cosmos. The journey from singularities and quantum bounces, through brains and multiverses to timeless emergent states, is not just a tour of theoretical physics. It is a reminder that the universe is infinitely richer and more surprising than we can easily imagine. It challenges us to expand our minds, to contemplate the extraordinary possibilities of existence, and to celebrate the remarkable fact that we are part of a cosmos capable of asking these very questions. In the end, whether the universe emerged from a pre-existing quantum vacuum, rebounded from a previous cosmic contraction, collided as part of a higher dimensional brain, or simply existed eternally in a stable state before expanding, the mystery remains. And it is precisely this mystery that fuels the pursuit of knowledge, drives scientific innovation, and inspires the timeless human quest to understand our place in the cosmos. By exploring what came before the Big Bang, we are not only unraveling the history of the universe, but also illuminating the remarkable chain of events that made life, consciousness, and curiosity possible. As we step back from the depths of these theories, we are left with a profound sense of awe. The universe, in all its complexity, beauty, and inscrutable origin, invites us to continue asking questions, to continue exploring, and to never cease marveling at the extraordinary reality we inhabit. The mystery of what existed before the Big Bang may never be fully solved, but the journey of seeking understanding enriches our knowledge, expands our imagination, and connects us intimately to the cosmos itself. It is a journey without end, and in that endlessness lies one of the most extraordinary truths of all. The universe is not only out there, vast and enigmatic, but within us, in our curiosity, our wonder, and our drive to comprehend the story of everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.